Good evening. I'm Bob Fishback, President of Chatham-Marconi Maritime Center. And I'm pleased to welcome you to the first Chatham-Marconi Speaker Series presentation of 2023. Tonight's topic, how might climate change affect New England storms, is particularly appropriate following the record-breaking storm which most of the nation experienced over Christmas, and as we here on Cape Cod enter the stormiest part of winter. Our speaker, Professor Emeritus Kerry Emanuel of Massachusetts Institute of Technology, is a distinguished meteorologist and climate scientist. He has recently retired from the Department of Earth, Atmospheric and Planetary Sciences at MIT and holds an SB degree in Earth and Planetary Sciences, as well as a Ph.D. in Meteorology, both from MIT. His career research interests have focused on tropical meteorology and climate, with a specialty in hurricane physics. As co-founder of MIT's Lorenz Center, he remains actively involved in climate research, which fosters creative approaches to learning how climate works. Following his presentation, Professor Emanuel will answer your questions. On your computer, enter your questions at any time by clicking on the Q&A tab at the bottom of your screen and typing them in. I will screen the questions and relay them to our speaker, and I may combine similar questions in the interest of efficiency. It is now my pleasure to introduce Professor Emanuel.
Well, thank you very much, Bob, and it's a pleasure to be with you all this evening. Of course, it would be a much greater pleasure if we were physically together, but we live in different times now. In any case, I'm privileged to be able to talk to you this evening about climate change, what it means in terms of risks, and I will use as an example of that the risks of large storms in places like New England. So without further ado, I'll share my screen. I assume you can all see that pretty well, I hope. So the title of my actual title is Climate Risks, Options, and Opportunities. And you might be a little bit surprised by the word opportunity, but I'm going to emphasize that. We usually talk about climate change as all doom and gloom, but it does present some very interesting opportunities for society, and I'll try to talk about those. So the program for this evening is, first of all, to give you a very quick update on climate science. If you're expecting a long tutorial on that, I'm afraid you might be disappointed. But to turn the subject rapidly to the problem of climate risks, and this is where climate change really does affect society, is in the risks that it presents, and I'll try to be a little bit more specific about what those are. How we go about in the scientific community trying to quantitatively estimate the level of risks from climate change. And then I'm going to turn, hopefully, an optimistic page to how do we go about solving this problem. And I will present the problem, as many problems turn out to be, as among other things, an opportunity. So let me begin at the beginning with the whole question of our influence on greenhouse gases and why they matter. And a little bit of a history lesson here. This really goes back to a very gifted, if dour-looking Swedish chemist, Svante Arrhenius, who lived toward the end of the 19th century and early 20th century, won a Nobel Prize in chemistry. But like a lot of scientists of the era, he dabbled in other things. And he's credited with the first scientist to begin to wonder whether our very rapidly increasing consumption of fossil fuels might change the composition of the atmosphere and how that might affect climate. And obviously, without the benefit of high-speed computers or satellites or any of the things that we have today, doing basically just plain physics, he came to the conclusion in 1906 that if we were to double the amount of carbon dioxide in the air, we'd raise the temperature of the surface of the Earth by about 4 degrees. And likewise, if we were to increase it by fourfold, the temperature would rise by 8 degrees. And again, this is elementary physics. A lot of times, the media present this as something that depends on some really, really complicated black box computer models that we have to sort of put blind faith in. That's very, very far from the case. We're really talking about elementary physics. And all we've been able to do in the intervening 120 years or so is to put error bars really on what Svante Arrhenius estimated way back then. Now, was he right? So this is, I'll let you decide. This is a graph showing in the first place the natural logarithm of the carbon dioxide concentration of the atmosphere, which we know very well from measurements beginning in 1958 and from bubbles of gas trapped in ice cores going back hundreds of thousands of years before that. Now, the radiative effect of carbon dioxide goes up as its log, so I plotted the log in red. And the blue is the annual temperature, mean surface temperature of the Earth, which we know pretty well going back to the end of the 19th century, and then it gets increasingly iffy if we try to go back much before that. So Arrhenius's prediction, in some sense, is that red line. And you can see that more or less the temperatures followed that, although it's had some other excursions. There's a lot of things going on, including other effects of burning fossil fuels, which tend to cool the climate, volcanoes, which also include it, and variations in solar output, all have an influence. But Arrhenius's prediction looks pretty good from where we stand, and the science behind that is rock solid. Now, if we go back in time, as I mentioned to you before, we can analyze the composition of bubbles of gas trapped in ice cores. And this is a graph going back 800,000 years on the left, 800,000 years ago, showing the carbon dioxide concentration in parts per million. And you can see that it goes up and down at periods of around 100,000 years. And these correspond almost precisely with our estimates of glacial temperatures, also partially due to analysis of ice cores. But carbon dioxide has gone up and down with temperature for a long time. And mostly, in the case of the past, it's the temperature change, which is really being caused by changes in the orbit of the Earth around the sun, that have caused the changes in carbon dioxide. But it doesn't have to work in that direction of causality. That spike that you see at the end of the record, that black spike culminating in the blue star, is the CO2 today. And there is zero doubt, literally zero doubt, that we did that, okay? There is no controversy about that. If you look at the isotopic composition of the CO2, it differs from what we saw in the past in a way that we expect, because this CO2 is coming from fossil fuels. So we are taking the most important long-lived greenhouse gas in the atmosphere and really spinning the dial on that. And it's hard to believe that you can do that without risk. Now, Arrhenius spoke in terms of doubling, but these are projections now of carbon dioxide going out to the future, beginning with the historical record back to 1958, this black dashed line. The blue dashed line, the horizontal line, is the concentration you get if you doubled CO2 from its pre-industrial value. And these different curves are just different guesses for what we're going to do to the CO2 content. That depends on the economy, whether we try to take measures to curb CO2 and so forth. But you can see that sometime around the middle of the century, we'll have doubled the concentration. It's a big deal. And if we don't do anything to stop this, we'll easily triple it by the end of the century. That's a really big thing to do to the most important long-lived greenhouse gas in the atmosphere. Now, what are the consequences of that? Well, the first thing I want to get across is that nature does have ways of taking excess CO2 out of the atmosphere. The problem is it takes thousands of years. Now, geologically, thousands of years is essentially instantaneous, but not for humanity. What this curve on the left shows is sort of a hypothetical modeling. What would happen if we just keep emitting, and then when it gets to some concentration, say 650 parts per volume, we suddenly turn off the spigot and watch what happens. And let's see what happens when nature takes care of it. Well, you can see that there's an initial fairly rapid decline over a few hundred years, and then it slows down and it takes thousands and thousands and thousands of years to go away. So unless we figure out how to suck CO2 in the atmosphere, it takes a long time for it to go back to what you might call normal. Now, this is on the lower graph, the corresponding surface warming, global average surface warming, going along with these CO2 curves. And these curves are much flatter, and that's because of the interesting problem of the uptake of heat by the deep ocean. A lot of physics in there. But to a good approximation, whatever temperature we reached when we finally turn off the spigot, and of course it's not going to be turned off suddenly, is the temperature we're going to be stuck with for thousands and thousands of years. So if we're going to do anything about this, we better act fast. Or we better figure out how to pull this excess CO2 out of the atmosphere. All right, so that's my Climate 101 in 5-second tutorial. Now I want to turn to the subject that I'm interested in and hope to get you interested in tonight, which why should that make any difference? Let me just say that we scientists aren't really very good at conveying why climate change is dangerous. And if we say it's going to warm up by 3 degrees, who cares? I don't even care. I can get 3 degrees by moving from Maine to New York very easily. That won't kill me. So why should we care about climate change? Well, it's all the things that go along with the temperature that we care about. But before I get to those things, I want to convey to you another very, very important aspect of risk, all risks, not just climate risk, risks we face every day, risks we think about when we're buying insurance. And this is a chart that's made from many thousands of computer simulations of the response of the Earth's surface temperature to a cooling of CO2. And so on this axis is the amount of warming, and on this axis, based on all those simulations, is the probability that we'll get a certain amount of warming. So that probability peaks somewhere between 2 and 3 degrees centigrade. Now, why are we talking about probabilities? Because there are a lot of uncertainties in projections. As you know, when we forecast the weather, we've gotten pretty good at it, but there are occasional busts, and we're never quite perfect. There is no attempt in the scientific community whatsoever to cover up the fact that there's uncertainty. Indeed, we try all sorts of different ways to convey it. But let's look at this curve more seriously. So there's about a 5% chance that the response to doubling CO2 will be less than about 1.8 degrees. That's over on the left side of this diagram. And that's, we probably would adapt to that pretty successfully. Then there's this big region between about 1.8 and 4.6 degrees, where the most of the probability is, and that's going to take a lot of adaptation, and there are fairly large risks associated with that much. There's about a 5% chance that will be more than 4.6 degrees or so. This out here would be truly catastrophic to human civilization. And so there's a real question of how much do we want to spend, if you will, to avoid this low probability but very highly consequential tail. So I want you to remember this kind of curve, which is how we try to convey in global terms what we understand about the future of climate. So little risk, substantial risk, catastrophic risk. It's going to be somewhere in there, folks, and that's what makes it an interesting and difficult problem. Now, just a little bit of math for those of you with a math background. If you don't have that, don't worry about this. There's a formal definition of risk. It's the integral of the cost of something over its probability. So let's say I is the hazard intensity. Cost varies with intensity, usually going up with the intensity of the hazard. And the probability of that, as we just saw in the previous graph, also varies with the intensity. Risk is if you multiply cost by probability and then you add it all up over the whole probability distribution. So for most risks, it sort of looks like this. This black curve is sort of the probability, and this red curve is the cost, and this is the magnitude. So for example, earthquakes. If you have a little tiny tremor, it's not going to do anything, right? And as you get stronger and stronger, the damage goes up. And if you start getting up into the 6s, 7s, and 8s, it really goes up steeply. And I'll talk about why that. So that's actually an anthropological point. But as the cost is going up, fortunately, the probability is going down, all right? And basically what you do to estimate the total risk is sum the product of these two numbers over this whole range. The important point here is if you're not certain about what's going to happen, that means this is a wider probability curve. There are more different scenarios that could happen because that increases the probability over here in this tail. That's where all the cost is coming from. That increases risk. So we would desperately like to reduce the uncertainty as climate scientists, but we have to live with what we know, and we have to be honest about what we know and what we don't know. So what are the risks? Well, as I just said, no one really cares whether the world warms up by 3 to 5 degrees. I don't. What we care about are heat waves, wildfires, hurricanes, droughts, floods, and things like that. As we've seen in the news, California tonight, as we speak, is being hammered by really serious floods after years of drought. But to really make progress, to ask ourselves, how much is it worth to us to try to avoid these? The first thing we need to do is quantify those risks, including their uncertainty, so that we have the basis of making an intelligent choice. Without being able to quantify the risks, we're just guessing, we're just shooting in the dark. One instrument, by no means the only instrument for conveying risk, and quantifying it, is insurance. And one big problem we have in society, not just in the US, but all around the world, is that current insurance premiums are based strictly on historical records of hazards like earthquakes and storms, not even accounting for the climate change that's already occurred. And the reason is you have to have 50 to 100 years of history even to take a shot at what the real risk is. If the climate's changing over that period, it makes it very difficult. But the good news is that science is positioned to make really rapid progress now into doing a better job of quantifying climate risk, including the risk that we already have because of climate change that's already happened. Now, when you do a long-term risk assessment, if you sort of add up the cost of any kind of hazards like earthquakes or hurricanes, it's always true that that cost is dominated by extreme events. That is fairly rare, but very powerful events. And it's an interesting anthropological point that societies are usually well adapted to frequent events. And frequent turns out to be, and I'll come back to this point, roughly more frequent than once in 100 years. Conversely, they're poorly adapted to rare events, which are less frequent than that. Well, this makes perfect sense because, for example, in Boston, a 30-mile-per-hour wind isn't going to cause any damage. We have that all the time. The 70-mile-per-hour wind is going to be really bad. That almost never happens, and we don't build infrastructure to deal with that. And that makes sense. If we did it, we'd be spending a lot of money to try to avoid something that's very unlikely to occur. The interesting thing is, why 100 years and not some other number? So we see large cost increases when something that used to be less frequent than about once in 100 years becomes more frequent than that. So let's look at that. This is a graph, and this is really a cartoon, but in fact, the real thing looks pretty much like this. It's percentage of property destroyed based on the magnitude of the event. Now, this could be an earthquake, it could be a volcano, it could be financial collapse in the markets. All kinds of risks have curves like this. And instead of plotting it versus the intensity, like the wind speed of a hurricane, I plotted it versus something called the return period, which is just a measure of the frequency of the event, whatever that event is. So 100 means 1 in 100. That is an annual probability of 1%. 50 means 1 in 50 years. And so for return periods substantially less than 100 years, very little property is destroyed. For things whose return period, they're so intense and so rare that they're spectacular, it's going to just wipe out everything. But the steepest part of this curve is around 100 years. And why 100 years? I don't know, but it's 3 or 4 human generations. And, basically it boils down to you know what hit you, you know what hit your parents, you probably know what hit your grandparents, and you probably don't know what hit your great-grandparents or beyond that. It's just a question of how much we know about our own ancestors. Now, I'm going to give you a concrete example here, and it is from my own field of tropical cyclone risk. And we're going to look at a study that we did actually for an insurance company, look at the probability every year that a certain amount of damage will be, or a certain amount of loss will be incurred to this insurance company that has properties all over the eastern US. You really don't need to know very much about it. But this is hurricane damage, if you will, and you read that off the bottom scale. It's in logs, so this is 100, this is 10,000, this is $1 million, this is $100 million, and this is $10 billion. So it goes up very fast here. And this is the probability. And so the most likely outcome in any given year, let's look at the blue curve here, is that this company would experience about $1 million loss from hurricanes or a hurricane. And the red curve is exactly the same thing, but it's been calculated for a future climate toward the end of this century. And you can see the probability has shifted a little bit to higher damages. And you look at that and say, well, that's not that much, okay. But I'm going to take the same data and to present it to you in a little bit different form by taking that probability and multiplying it by the damage itself. And that's a quantity called risk. And here are the two curves, all right? And this time, the total expected damage over a long period of time is proportional to the area under these curves. And you can see that it's quadrupled when you go from the climate of the late 20th century to the climate of the end of this century. And you can see that that's happened for events that are in the $100 million range for this company. And that, to go backwards, is all occurring out here in the tail of the probability distribution. This is the infrequent events that really get you. And so this is why we're worried about climate change. It really affects the tails of the risk distribution where most of the damage comes from in the long run. Okay, the problem is if these 100-year events are so important, how much data, historical data, does it take to estimate how likely they are? Well, about 1,000 years. All of the, your insurance premiums, if you're paying insurance premiums for your property, are based on no more than 100 years of records. And that's enough when things like house fires, because there are a lot of houses and there are a lot of fires, and we have very good statistics. For storms, it's not even close. The historical records are flawed and they're pretty short, particularly outside North America. And the real problem is, even if you had perfect historical data, the last 50 to 150 years that you have these records for is a poor guide to the present because of climate change that's already happened. And I can't emphasize to you enough what serious problems we're in today because of climate change that's already happened. You don't have to believe in computer models, whatever you like, but the climate has demonstrably changed, and it's really upset our estimates of what the true risks of weather hazards are. Unfortunately, the professionals who estimate this risk are so vested in the approach of the old days of basing this on historical records that they're making a lot of money. They don't need to migrate to some other approach. But I advocate, and many of my colleagues, that we need to get away from that and base our approach on physics and not just history. And I'm going to give you an example and try to make it as concrete as I can in my own field, which is quantifying the risk of hurricanes, okay? And let's just talk about, how risky they are. Well, since about 1970, on average around the world, they kill about 10,000 people. $700 billion in damages done globally in 2015 dollars since 1970 or so. And then the really scary thing for us is demographic. The global population exposed to hurricane hazards has tripled since 1970. And believe me, the population of the planet hasn't tripled. It's just that people are moving, not just in the US, all around the world, like lemmings to the coast. And there's some very interesting reasons for that. Well, is the risk of hurricanes changing, or do we have data to suggest that it is? Well, one thing we can look at is how much damage hurricanes do around the world. And this is a chart of the global damage divided by the world domestic product. It's what fraction of the world domestic product is damaged by hurricanes. Fortunately, it's a small number. You have to multiply these by 10 to the minus fourth. But it's inflation proof because both of these things go up with inflation. And you can see that there's a pretty healthy upward trend, about a 380% increase since 1970. But that is mostly driven by the statistic I just cited of people moving to the coast. There's just lots and lots of people moving to places where they can get clobbered by hurricanes. The population has increased, as I mentioned, by 200% or a factor of 3. And there's a suggestion, but no proof, that the rest of it may be due to climate change. But we do have other data that suggests that the risk of hurricanes is increasing. This is a chart going back to about 1900, showing the number of major hurricanes in the Atlantic basin. The blue curve is from historical statistics of hurricanes. Fortunately, we have some anyway going back that far. And the red is from an approach to modeling hurricanes, which I'll talk about in a minute. And the red shading shows that it's more complicated, the expected error in the historical observations. On the other hand, if we look at the total number of tropical cyclones in the globe, we can only go back to about 1980. Before that, places like the Pacific Ocean, you could have lots of hurricanes you never even knew happened. It wasn't until we got satellites that we really started to nail the global frequency. And you can see that it's about 90 per year, and there's no significant trend in that number. On the other hand, if you look at satellite data, this graph, again going back to 1980 and globally, shows the proportion of hurricane observations that are of major hurricanes, that is, hurricanes of category 3, 4, and 5. And that proportion has been going up over this period of time, and it was predicted to go up way back in 1987 just based on very simple physics of hurricanes, that this really ought to happen. Even though we don't really know what controls the frequency, we do expect the intensity to go up as we put more carbon dioxide in the atmosphere. But on the other hand, these records are just vastly insufficient to really estimate the quantitative risk of hurricanes and how that risk might be trending. So what we have been trying to do at MIT and a few other places is to bring physical models to bear on risk estimation. Now, what is a physical model? It's basically an algorithm that solves the known equations for the behavior of fluids, thermodynamics, radiation transfer, solves those equations on a computer so that it's really a deterministic algorithm. We started to develop those in the 1950s to forecast the weather, and we've gotten steadily better. And so what you see on the left, that, by the way, is my ship's clock to remind me that I'm near the ocean here in New England. We have the satellite image on the left, and we have a forecast by a global weather forecast model, and it's becoming increasingly difficult to tell the difference between the two. This chart is showing you a measure of the skill of global numerical weather forecasts from 1981 to 2018. The blue is for a 24-hour forecast. It's for a 3-day forecast. The red is for 5 days, the green is for 7 days, and the yellow is for 10 days. And we basically had no skill in 10-day forecasts until about 20 years ago. But you can see, and by the way, the lower curve is the southern hemisphere and the upper curve is the northern hemisphere. It's easier to forecast the northern hemisphere because we have a lot more observations there, but because of satellites, that gap is closed. And you can see that a 7-day forecast today is as accurate as a 24-hour forecast was in the early 1980s. That's real progress. And by almost all metrics, weather forecasts have gotten better. And it is basically a climate model is pretty much the same as a forecast model, although it has physics on it that operate on longer timescales. Unfortunately, we can't use global models to simulate many of the phenomena that really present the risk to us, hurricanes being an example. And I'm showing you in this chart the frequency of hurricanes in the Eastern Pacific as a function of how strong their winds are. And the black is from actual observations of hurricanes. That vertical black line is divides category 2 and below from category 3 and above. Virtually all the destructive hurricanes are to the right of this line. The red is what we get from climate models, state-of-the-art climate models. We don't even simulate the hurricanes that are destructive. That's just because we're not able to resolve them. Our computational lattice is too coarse to do that. So what we've done at MIT is to figure out how to embed within climate models very, very highly resolved hurricane models. It's a long story, and I'm not going to bore you with it. If you're interested, you can write me, and I can put you on to some literature about this. But it's possible to take a given climate represented by a climate analysis or a climate model and produce 100,000 or so hurricanes from those models using very advanced physical techniques. To give you an example, here is a synthesis of only about 3,000 hurricanes that have been filtered only to include those that cross the coast of New England, broadly defined as New York City to Eastport, Maine, okay? And so these are the top 50 in terms of their intensity when they cross the coastline. The wind speed is color-coded in knots. I know if you're tuning into Cape Cod, you know what a nautical mile per hour is. The blue dots show where each of these tracks start. This is just the top 50 out of 3,000. So you can see that the really monster storms tend to come at New England from the south and the southeast. Now we can use this basically to downscale climate models run during the 20th century and compare that to models run, say, toward the end of the century. And that's what's done here using downscaling seven different climate models. This shows the return period on the left. So the higher this is, the rarer the event, versus the maximum wind speed that it has when it crosses the coastline. So the blue is for the end of the 20th century, 1985 actually to 2014. The red is for the last 30 years of this century, and the shading shows the scatter among the climate models. As I've emphasized to you, nothing in the climate business is certain. We try to quantify that uncertainty. The red and the blue shading show our estimate of that uncertainty. So the way to interpret this curve, say if you look at 64 knots, which is the division between a tropical storm and a hurricane, that would occur somewhere along the coast of New England every 5 years in the current climate, but only every 3 years, or as much as every 3 years in the future, if you look at the mean amongst all these different models. 100 knots, which occurs very seldom in the current climate, would occur roughly every 14 years or so in the future. Now, if we take a particular point, of course, to get a strong wind from a hurricane at any given point is a very rare event. I chose Marconi Beach in honor of this talk, same 7 models. If you wanted to actually experience 100 knots of wind right at Marconi Beach, and you weren't willing to walk up or down the beach to experience it, you'd have to wait about 3,000 years. But toward the end of the century, that's down by an order of magnitude, 200 years or so, okay? So there is the prediction of substantially increased risk from hurricanes along the New England coast. This is the same kind of statistic, but not for wind, but for total rainfall. And I chose the city of Worcester. In New England hurricanes, a lot of the heaviest rain falls to the west of the tracks of the storms. If you wanted to see 10 inches of rain from a hurricane, in Worcester, you'd have to wait forever. But toward the end of the century, toward the end of this century, it might happen once a century or so. Another thing we can do with the model is couple it to hydrodynamic models that predict storm surge, which often is not so much in New England, but in the tropics, the real big killer in hurricanes. And include the estimate that by the end of the century, level generally be about a meter higher. So if we include that together with the hurricane-induced storm surge, this is a little bit different chart because this is frequency now on this axis versus the peak surge in Boston Harbor. If you wanted to see 2 meters or about 6 feet, you'd have to wait forever in the current climate, but it might happen with this meter rise in sea level every 20 years. And this is a big problem because these events would flood a lot of downtown Boston. They almost never happen from hurricanes. Today, you do get flooding from nor'easters, which I haven't talked about, but is a big problem in New England. But from hurricanes, you're going to see probably more flooding. So is this our future? Are we going to have to live with a scenario like this? This is just a recreation of what downtown Boston, Back Bay, and Cambridge might look like if we got this level of surge. Okay, so what are we going to do about this? The first step is to assess these risks. I've just talked about that. Once you have some assessment of flood levels and wind, you can couple these to models of how much damage these hazards would do and assess the economic risks. You can also assess other kinds of societal risks. Then once you know what the numbers are, you're in a position at least to begin to formulate policies to address the risks. And to do this whole thing in an intelligent, rational way, you have to account for the uncertainty at each step in the process. Here's an example done by my colleague Solomon Siang at Berkeley, showing this is very ambitious for the entire planet, the expected direct damages from climate change in the period 2080 to 2099 as a percentage of the world domestic product. And for different these RCPs are different estimates of carbon dioxide emissions, with the red being the largest. And you can see that maybe for 3 degrees of warming, you would expect about a 2% hit to world domestic product. Well, that doesn't sound like a lot, does it? 2%, you know, it's not like 20% or 80%, it's 2%. Probably we could live with that. Well, you'd think so. But let's look at what that's done historically. So this is the real GDP per capita between 1900 and 2017. So you can see a steady rise. This is for the US, a steady rise in GDP. Well, not quite steady. It was interrupted, first of all, by the Great Depression in the 1930s. At the peak, it was a 3.3% drop. It averaged over 10 years, maybe 1.5%. So a few percent drop in GDP sustained for a long time is a real hit to the economy. And I would point out 2 things. This 2% estimate of loss of GDP, say for 3 degrees of warming, is going to be sustained over many, many years. And the co-author of the paper that produced this data is that people don't really appreciate that this is compounding. It's a few percent per year compounding. The other thing is that there's an actual spike in GDP during World War II. And at its peak, the US was spending, get this, 40% of its GDP on the war effort. So it doesn't follow that spending a lot of GDP on something that's not exactly productive for all of us as individuals, like fighting a war overseas, doesn't necessarily ruin the economy. Now I'm going to say something that might strike some of you as almost Machiavellian, but I really do mean it, that where there's risk, there's opportunity. And so the real opportunity, I would argue, is in the transformation of our means of generating electricity, energy in general. The current global annual energy market's $8 trillion. That's huge, okay? Big percentage of US GDP, for example. Moreover, there's large expected growth in this number because the developing world is actually developing. We have China as an example, and India, and probably Equatorial Africa to follow. And it is true that energy is very slowly being decarbonized. So if we can figure out how to do that faster, people, nations, and industries that can innovate clean energy will become market leaders. So there's a lot of opportunity. And it is a good time for various nations, the US, for example, to try to catalyze this energy innovation. Now let's take a quick look at the solutions and opportunities. Well, for energy, there's a lot of excitement about solar and wind. Indeed, the prices of solar photovoltaics and wind turbines are falling rapidly. And at low market penetration, below about 30%, if you're generating less than about 30% of your power from these sources, the intermittency that's inherent in solar and wind can be dealt with through baseload, which today, unfortunately, is mostly coal and natural gas. But I would point out that because there are times when both the sun doesn't shine and the wind doesn't blow, you have to have the full baseload capacity ready to go. So all the costs that go along with maintaining capacity, you're not saving anything from that kind of maintenance costs by renewables. If you wanted to go with these kinds of things to high market penetration, then you're going to have to rely on storage. But the problem is that right now, the best current and near-term projected method is lithium-ion batteries. To get 12 hours storage capacity, it's about $4,000 per kilowatt hour, and that's projected for 2025. By 2040, we're going to need 5 trillion watt capacity globally to take you over a mere 12 hours. That'll cost about $1 trillion per year for 20 years. So when people say that renewables are the solution and point to rapidly falling costs, they're not telling you the full story. If you want to get up to large market penetration, you're going to have to store, and we can't really afford that. Moreover, the current lifetime of lithium-ion batteries is only about 10 years. Will this improve? Yeah, certainly. How much are you willing to bet on large improvements is a personal choice. That actually will add, this current lifetime limitation adds about 2 trillion to maintenance costs. And again, you're only buying 12 hours of storage. So it's really expensive unless you're just using it up to about 30%, and then it really is economical. So there's a niche for that. On the baseload side, if you want to have carbon-free, the current option is nuclear fission. Projected electricity demand is equivalent, if we're going to do it all by nuclear, and of course you won't. It's equivalent to about 2,500 2-gigawatt reactors, and you need to build 125 per year for 20 years to do that. We know from experience that to build one of them in South Korea, who know how to do it efficiently, it's about $4 billion. So that's 500 billion per year for 20 years. That's about 6.6% of world domestic product. It's serious numbers. But the good news is the service life of one of these reactors is on the order of 80 years. You don't have to keep replacing them that frequently. And in some sense, we've already done it at that rate. In the 1970s, Navy Sweden built one 4-gigawatt reactor per 10 million residents per year. If you could scale that up, that would give you 750 4-gigawatt reactors per year for the global population, but you don't need that many. It's more like 125. But we don't have to rely on 50s fission technology. There's lots of experiments going on with molten salt reactors, which are passively safe. Some of them can help process waste from existing reactors. They operate at ambient pressure, so you don't have a lot of the risk associated with very high pressure. You can run it on thorium, which is much more plentiful than uranium and somewhat less suitable for making weapons, and again, has a long lifetime. One of the great myths about nuclear is dangerous. The opposite is true. It's the safest power we've ever generated. No, I'm not a nuclear engineer. No, I don't really care about nuclear versus solar versus wind. I'm just looking at the facts here. This is the mortality per kilowatt hour generated. It's actually 100,000 lives lost per trillion kilowatt hours by source. Coal is king. Coal kills, coal and oil and gas from particulates kill about 8.7 million people per year globally. Oil, coal, gas, then you go down to hydro. Nuclear is the safest by far. That's just a fact. So there are 13,000 premature deaths annually in the US from coal production and combustion, 8.7 globally. If you said that solar power killed 9 million people a year, would anybody do it? No. Or any of these other hydro, wind, nuclear, but we're happy to live with it for coal because we've done it for so long. It's a quirk of human nature. So this is an interesting statistic. I like to tell my environmental friends, more people die every 3 days from fossil fuel particulates than have died in the whole history of nuclear power. Yet, this is the one everybody identifies as the most dangerous. This is frustrating for a climate scientist because we do know how to solve this problem, but we have disinformed ourselves so much about this that we're not going to make progress. But there are non-climate savings from eliminating fossil fuels. It's not just that they help the climate. World Health Organization estimates 4.2. That's been up to more recently at 8.7 billion. Sorry, it shouldn't be dollars there. It's 8.7 billion. Oh yes. No, there's something wrong with this. It's 8.7 million people, not $8.7 billion. The global economic value of life, I don't have any idea how economists come up with these numbers, but it's estimated to be 100 grand globally. So we'd be saving about $400 billion per year in the economic value of saved lives if we could get rid of fossil fuels. That's an opportunity. And even if you don't care much about climate change, it's an enormous opportunity to live better. And if we applied that to nuclear, we're talking about if we put the savings onto the loss side from building these reactors, it's about 0.1% of world domestic product. And this is really important to me, is that cheap green energy, green meaning no CO2, would permit large increases in per capita wealth in the developing world. In other words, it's a key to eliminating or reducing poverty. The energy conversion would likely yield net benefit even before we consider climate change. Climate costs, if we keep going down the road we're going, could be very large, estimated at as high as $3 trillion a year by the end of the century. So yeah, it would cost something to do something about this, but if we don't do something about it, it's going to cost us a lot. Let me summarize. We're altering the composition of our atmosphere at considerable risk to ourselves and to future generations. There is no doubt in my mind about this, okay? Considerable risk. Remember, risk has uncertainty associated with it. That's the nature of risk. The long-term risk is dominated by extreme events. That's true in all kinds of spheres, not just climate ones. The historical records that we're now using to estimate things like insurance premiums are inadequate for estimating just the current risk. I mean, for example, the rains from Hurricane Harvey, 3 different independent groups of scientists estimated that probability of that event had tripled since 1970. Tripled. We're not talking about a few percent. We, in the scientific community and in the risk modeling community, should embrace advanced physical modeling techniques for assessing these risks. It's absolutely necessary for us to try to quantify that. And I would say, based on the analyses that have been done, that the quantitative assessments of climate risk to the economy warrant spending at least 2% of world domestic product on mitigation. And yet for all of the risks, like what you're paying for your insurance premium on your home, if you have one, if you own one, we are willing to spend somewhat more than the estimated long-term cost of the risk. That's called a risk premium. The good news is if we use optimal combinations, and this is, I'm not an energy expert, but virtually all the energy experts, certainly those at MIT I talk to, say this: optimal combinations of nuclear and renewables, it's a golden combination. It would be feasible to decarbonize at least electricity at about 0.5% of world domestic product, and all energy, that is energy including things that are not electricity, at about 2%. I'll leave you with those thoughts, and I'm happy to take any questions.
Okay, thank you, Dr. Emanuel. I'm still absorbing. I consider myself a recovering engineer, so I'm a little slow on the uptake here. We do have some questions. The first one is from Hilton. He asks, he or she, isn't it true that the cost of solar and wind are even higher than you showed because of the massive cost of distributing energy from the solar and wind generation sites?
Yeah, that's a very interesting question, and there's a real issue about how you add up and tally all of these energy costs. And a lot of that depends upon how the solar and wind resource is distributed in space. But yes, transmission is a big cost, and it's an argument that's been used, for example, on the positive side, to support the notion of a lot of something called small modular reactors, where you can distribute them much more broadly, especially in places that don't have a lot of sun and wind. So yeah, that will tend to increase the costs more.
Okay, thank you. David asks, since insurance companies are quite inadequate at modeling, are we going to see very significant increases in cost or loss of coverage as they recognize the risk of climate change? I believe this is what's called a leading question.
Well, I actually sit on the boards of 2 insurance companies, and I've had for years, so I get to hear what all their issues are. What I think you're going to see in the United States and elsewhere is what you might call a re-rationalization of insurance, redistribution of premiums. So if you're living in a risky place, like the south side of Cape Cod or anywhere along the eastern seaboard within a few miles of the beach, you're likely to see your premiums go up. If you're living in a non-risky place, you might actually see your premiums go down, because right now, the only way the insurance business stays afloat is the government quietly allows them to overcharge, not by a lot, but huge numbers of people are paying a little bit too much to subsidize a few people living in risky places. And that has the bad societal effect, encouraging this migration. If you're being subsidized to migrate, in effect, encouraging the migration into risky places. And people are beginning to understand that that's not a really good idea for any society. How this all plays out, just one comment. I was looking at a new kind of insurance instrument that they're thinking about offering, which will pay you if your house is demolished by a hurricane, but only if you agree to move. So there are kinds of gimmicks like that being imagined.
Okay. Next one. Frank and Carolyn ask, how do we translate the reality of this science into communication tools to educate the general public and non-science oriented elected officials?
Well, that's the $64 million question. And I've spent probably the last third of my professional life trying to figure that out. And the reason I'm here right now tonight is part of my efforts to do that. But, it has to happen on a massive scale. The problem I think we have is that the climate, until very recently, the climate change risk was not seen as immediate by most people. It's football you could keep kicking down the field. But people are beginning to wake up. For example, the insurance industry has woken up to the fact that it is really getting hammered because its current estimate of current risks is way off because of the climate change that's already happened. And as more and more people wake up to see that they're already at risk, attitudes are beginning to change. And what I see is this giant ship of public opinion, which includes the public itself and their representatives, is beginning slowly to change course. And the question is, will it change course fast enough to really avert some of the worst risks that we face?
Okay, I have a couple more questions along the same line. I'm just curious, you talked about the need for energy storage, which we're all aware of, I think, to supplement cyclical sources like wind and solar.
Yep.
Is there any advantage or disadvantage to distributing that storage to, say, to residential units, businesses, as opposed to mass storage concentrations of
Well, that
battery
depends.
power?
That's a great question. That depends very much on the technology. For example, I know at MIT they're developing batteries where the major element is actually just plain old ordinary iron. But it turns out that technology only makes economic sense if it is extremely centralized. So it wouldn't work to put an iron battery in every house, at least not with the current technology, where if it's lithium ion, there's sort of an optimal distribution of storage, and I don't understand enough about the problem to be able to tell you what that is. But I can say safely that people have given that important point a lot of thought.
Okay, we have a few more questions. John asks, you mentioned if we could suck CO2 out of the atmosphere, is that a possible reality? Is that technologically feasible in the future?
It's certainly technologically feasible right now, and there are various experiments being done. I happened to visit Iceland this past July. There's a big experiment to draw CO2 out, let it react with the very plentiful basalt rock that island is made of, and that reaction produces another rock called carbonate, where all the carbon is stored, and it's not going anywhere. It's not going to go back into the atmosphere. The problem is it's way too expensive. We can't do it. We can't afford to do that now at scale. There are fundamental limitations on how efficiently you can do that. But it's interesting enough that we need to keep funding research on it. Right at the moment, it looks a bit bleak, but we have to knock on all the doors at this point.
Good. I have two questions that I'm going to combine here, and you can swing for the fences or bunt. Your option. Reed and Jane ask, what about nuclear fission? And an anonymous attendee asks, is there any real appetite for nuclear power in the United States or other nations?
Okay, I think maybe the first question was, what about nuclear fusion? Because I did talk about fission. And
fusion, I think they meant fusion, yeah.
Yeah,
Sorry
there's a lot of optimism. For the first time in my career, there's a lot of optimism about fusion. As you might know, a few weeks ago, they finally broke a record where they produced more energy than they used in experimental fusion reactors. But there's a lot of optimism that on a time scale of 15 years or so, we're going to be able to do economical fusion. And I'm sorry now, of course, I've forgotten the second question.
Well, how much appetite is there among the public for nuclear power here in the U.S. or in other nations? And let me add a footnote to that. You're relatively local. Maine is not that far away. You may be aware that here on Cape Cod in eastern Massachusetts, there's been a lot of concern over the last couple of decades about the nuclear power plant up in Plymouth, Massachusetts, which is now discontinued and put out of business. There was a group here called the Downwinders that spent a number of years trying to make everybody on Cape Cod worry that we were all going to get fried if there was a nuclear accident in Plymouth because we were downwind of the plume. And what seems to me is they've done is succeed in scaring the daylights out of a lot of people in the public who don't understand the realities of nuclear power. And that goes along with Mr. Anonymous's or Ms. Anonymous's question about how much appetite in the US is there for nuclear power expansion.
Well, there's actually that has changed a lot in the last 10 years because people are waking up to the fact that it could avert a much larger risk, which is the risk of climate change. I think the problem is almost a psychological one. That Plymouth plant had to be shut down. I was actually in favor of shutting that down because it was at the end of its useful life. It was just old. Okay, it wasn't. It's not that there shouldn't be nuclear power. It's that particular plant, there are reasons why it should be shut down. If we were to really build out nuclear power, the idea that there would never be an accident anywhere is, I don't think that's attainable. There would be, okay, there would be occasional accidents. The problem, of course, is that people greatly overestimate the actual loss of life and damage from it. It's, people live under the glide paths of airplanes. And once in a while, once in a blue moon, there'll be a crash and people on the ground will die. And your chances of being hurt by an airplane crashing on you are actually larger than the chances of you're going to be affected adversely by a nuclear power plant. And yet we don't worry about that risk. We put it down to, well, we need to fly and it's a low risk. But we don't take that attitude to nuclear power. And it's because of a lot of sort of demonization and mythology that's gone along with it. But it is because of this, on the other hand, the flip side is it's really become very, very safe. But to make it that safe, it's become hideously expensive. And that's the real problem with it in the US. That's why I quoted numbers in South Korea, where they're building them very efficiently and running them very efficiently. Right now, it's way too expensive because we've made them in a sense too safe, I would argue.
A similar question, and then I have just a couple of questions, and then we'll wrap here. And I want to thank everybody who has submitted questions. Along the same lines, Douglas asks, regarding small nuclear plants, they are much harder to keep secure than large centralized plants. Your comment on the cost impact of that trade-off.
Yeah, I think, you wouldn't want to do that with pressurized light water reactors. And in fact, I don't think that's the basis of most of the designs I've looked at anyway. So for example, the thorium-based reactors, the molten salt, it's much harder. It's not impossible, but it's much harder to weaponize the fuel that goes into those. In fact, thorium is only fissile and not much beyond that. So, you have to do the math, and I've looked at these numbers. It's you can't drive that concern to zero, but it's pretty small.
Let me swing the next question back to away from nuclear. David asks, could future building codes produce stronger structures by creating models that incorporate higher load levels as opposed to adding strength to current plans? I'm not 100% sure what he means by that. Aim for a stronger structure to begin with, as opposed to adding to the current model. Not quite sure where that's coming from.
The answer is yes, you could make buildings almost indefinitely strong. The problem is at what cost. I was involved in a study about 10 years ago where we were looking at New York City, and we were asking, and this was not for wind, but for flooding, what would be cheaper to do? Harden buildings to be more, flood proof, or to build a great big storm barrier between New Jersey and Long Island to prevent the flooding in the first place? And the answer to that question depended upon your time horizon. If you're only worried about the next few decades, it's far cheaper to harden all the structures that you're dealing with. If you're worried about the end of the century, it's cheaper to build the seawall. So the answer to your question, it's a very good question, is going to depend very much on the local situation and on the time horizon, what you should assume about discount rates in the economy and so forth.
Okay, thank you. I have a wrap-up question that's a bit of a softball. Where should people go to get more information about your talk this evening, if they want to dig into it a little deeper, dig into the subject?
Well, there are a couple of resources I could recommend. I have a small informal book you can read in about one sitting called What We Know About Climate Change. It's a little book. It doesn't cost very much. It's MIT Press. I think it's in its 3rd or 4th edition now. I have, if you just type my name into Google, you'll find my homepage. And on that homepage is an online free climate primer, which is aimed at a little bit higher level, but I think it's still accessible, and it doesn't really talk about none of these things. Well, what we know does go a little bit into the energy solutions, but the climate primer is strictly science. And there's an online version that MIT hired some fancy web people to do called just, if you go to MIT and look for climate primer, all one word, I think you'll come across it. I have a bunch of essays on my homepage on the nuclear issue as well.
Very good. Thank you. I want to thank you for your time tonight and for this wonderful information and this wonderful presentation. I'm going to see if I can keep this in the camera here. And we're going to present you with our Chatham Marconi logo hat. The camera is defeating me.
But we can see glances.
Happily send it along.
Thank you.
As a token of our appreciation. And to our audience, I want to thank you for joining us tonight. This program has been recorded, and in a few days will be available on our website, chathammarconi.org. Join us on February 2nd, when Dr. Ed Moxon will present Cape Cod's Fabulous Radio History, Facts to Remember and Fictions to Forget. Information about the center, Marconi RCA Wireless Museum, our summer STEM program, for which registration is now open on our website, and our events are also available on the website. Thank you again, and good night.